Exponential functions. We'll start by considering an application. Bacteria reproduce through a process of binary fission, during which one bacterial cell splits into two. Under certain conditions, bacteria can reproduce very quickly. The following is a table that represents a culture beginning with one bacterial cell that divides every hour. So here in my table, time t is given in hours, so I have time in hours between 0 and 10 hours, and b of t represents the number of cells of bacteria. So we were told we start with one bacterial cell at time 0, and that cell divides every hour. So at time 0, I have one cell of bacteria. At time 1 hour, I have 2 cells of bacteria, and each of those 2 cells split. So at 2 hours, I have 4 cells. At 3 hours, I have 8 cells. At 4 hours, I have 16 cells, and so on. And I can see that at 10 hours, I already have 1,024 bacterial cells. So notice here how quickly the bacteria grows. If we compare this to a different model, a certain species of bamboo that is known to grow quickly at 1 inch per hour. The following is a table that represents a certain bamboo plant that starts at 1 inch tall and grows 1 inch per hour. So in this second table, I have time represented in hours, and h of t is the height of the bamboo, and that's in inches. So we have at time 0, the height of the bamboo we're tracking is 1 inch tall, and it grows 1 inch per hour. So at 1 hour, it's 2 inches tall, and at 2 hours, it's 3 inches tall, and 3 hours is 4 inches tall, and so on, so that at 10 hours, it is now 11 inches tall. So from a previous lesson, we know our bamboo data is linear because the original value from the range, from the outputs, increases by the same amount over equal increments found in the domain. So let's pause and think about that. So we have the values in the range increase by the same increment. So they're going up by +1 every time. And that happens over equal increments in the domain. So my domain is going up by 1 hour every time. +1, +1. So that being said, we can model the height of the bamboo as a linear function as h of t equals 1t + 1, or just t + 1. So the slope is just 1. So we could compute the slope by doing the change in y over the change in x. And the y-intercept is 1 because the y-intercept represents the initial value. So my bamboo started at a height of 1. Now the question is, how do we model the data for the bacteria growth? So if we go back and consider the data, well, over the domain, we still have equal increments. So I'm going up by 1 hour every time, so I'm going +1 hour, +1 hour. But the change in the actual count of the cells of bacteria isn't additive. So I'm not increasing by the same amount every time. So if we recognize the pattern here, to get from 1 to 2, we are multiplying by 2. So times 2. To get from 2 to 4, we're multiplying by 2. To get from 4 to 8, we're multiplying by 2. And that's because each cell divides, and so we're multiplying by 2 every single time. So in order to model that data, we need an exponential function. So the bacteria is modeled by b of t equals 2 raised to the power of t. And we'll look more closely now at a general exponential function. An exponential function is of the form f of x equals a times b raised to the power of x, where a, x, and b are all real numbers. A cannot be equal to 0. B has to be positive, but b cannot be equal to 1. A has a special name. It is the initial value. So in other words, when x is equal to 0, because if I plug in x equals 0, anything to the 0 is 1, and so all I'd have left is a times 1. So a is the initial value when x equals 0. B is called the base of the exponential, or sometimes called the growth factor. And the domain of an exponential function is all x values in negative infinity to infinity. So I can go ahead and make the exponent any number I want. So here are some examples of exponential functions. So I have y equals 3 times 4 to the x. I have y equals 1.5 raised to the x. I have y equals 3 to the quantity x plus 1. So that x plus 1 that's up there, that is fine. That's just going to give me a shift in my exponential function, so still considered an exponential. And then y equals negative, and then the quantity 1/2 raised to the power of x. So all of these are examples of exponential functions. Now let's look at some that are not exponential functions. If I have y equals x squared, so here this is just a quadratic, or more generally a polynomial, when I have the variable x in the base and a number in the exponent. So our exponentials have the opposite. I have a number, a real number in the base, and the variable x to the first power in the exponent. Now, y equals 1 to the x is not exponential because we had this restriction that the base could not equal 1, because then this is really just a constant function, y equals 1. It doesn't matter what x I plug in, 1 to the 10th is just 1. So this is not exponential, this is just a constant. Y equals the quantity -2 raised to the x. This is not exponential because the base has to be greater than 0. And then finally, y equals x to the power of x is not exponential because I need a real number in the base. I can't have an x variable in the base and then x variable in the exponent as well. In this example, we're going to start by determining which of the following represent exponential functions. If exponential, find their base and initial value. If not exponential, how can you describe them? Part A, we have f of x equals 2 times the quantity 4/5 to the power of x. So this is exponential. I have real numbers for the value of a and the value of b, and b is positive. So we do have an exponential function. So I'll go ahead and put exponential, check. The initial value, a, is positive 2. So the 2 that's in the front here, that's my initial value. So I can also think about it, what happens when I substitute in x equals 0? Well, 4/5 to the 0 is 1, so what I have left is 2. And then my base, b, is 4/5, the quantity that's being raised to the x, so 4/5. Now, just a quick note, I cannot multiply this 2 and this 4/5 together. So I have to think about order of operations, which says address exponents first. So I can never multiply this a value, my initial value, times the base when there's that exponent of x up there. Now, in part B, I have y equals -3 times x to the 4th power. So this is not an exponential function. I don't have a number in the base and a variable in the exponent. So this is not exponential. But we can go ahead and classify it as a polynomial. So this is a polynomial function. Or more specifically, I can even get a little bit more specific, this is a power function, right? Or a quartic function. So we have a lot of different labels that we can start to give our functions now. In part C, instead of being given an equation, I have a table. So I have x values, -1, 0, 1, and 2, and my f of x values, my outputs, are 4, 8, 12, and 16. Well, my domain values increase by 1 every time, and my output values are growing, I'm adding 4 every time. So since I'm adding the same number every time, that means that I have a linear function represented here. So this is not exponential. So I'm going to go ahead and put that this is not an exponential function. Whoops, not exponential. And this is actually a linear function. So really generally, this is a polynomial again, but it is a linear function. And then in part D, I have another table where x values increase from 0, 1, 2, 3, so increase by 1 every time. And my outputs, f of x, start at 3, and then I have 1, then I have 1/3, then I have 1/9. So what's happening here is to go from 3 to 1, I'm dividing by 3, and to go from 1 to 3, I'm dividing by 3. So another way to think about that is multiplying by 1/3. Division by 3 is the same as multiplication by 1/3. So to get from 3 to 1, I'm multiplying by 1/3. To get from 1 to 1/3, I'm multiplying by 1/3. To get from 1/3 to 1/9, I'm multiplying by 1/3. And so since we're multiplying by the same number every time, that means we do have an exponential function. So we do have an exponential function here. The initial value, so a in this case, is going to be 3. And that's because it's the value that corresponds to when x equals 0. So a is equal to 3, and b is 1/3. So my growth factor is 1/3, what I have to multiply by every time to get from one value in the range to the next. Now in this example, we want to find an exponential function that passes through -2, 6 and 2, 1. So we have 2 coordinate points, and we want to find an exponential function that passes through those 2 points. So we'll start by remembering what the general form of an exponential function is, a times b to the x. So what we can go ahead and do is recognize that in being given coordinate points, we're being given x values and y values. So I'm going to go ahead and substitute in my x and y into my general exponential form. So when the output is 6, I have a times b to the -2. And so that's not quite enough to solve for either a or b. I have one equation that involves 2 variables, but I can go ahead and use the other coordinate point as well. So when y is equal to 1, I have a times b to the +2. So now I have essentially a system of equations. So what I can do is solve one of the equations for a particular variable. So I'm going to use the substitution method. So I'm going to focus on the equation 1 equals a times b squared, and I'm going to solve it for a. So if I go ahead and solve it for a, I have a is equal to 1 over b squared. And with substitution, we then take that value and substitute it into the other equation. So I have 6 is equal to 1 over b squared times b to the -2. And at least this equation now has all the same variable. That's the goal. So b to the -2, well, that's 1 over b squared, so I have 1 over b squared times 1 over b squared is equal to 6. And we can multiply these together, so I have 6 equals 1 over b to the 4th. And so now I can go ahead and think about this as cross multiplying. This is like 6 over 1 equals 1 over b to the 4th. So I end up with b to the 4th times 6 is equal to 1. And then I'll divide by 6, so I have b to the 4th equals 1 over 6. And now to solve for b, I have to take the 4th root of both sides. So I have b is equal to the 4th root of 1 over 6. Now, This is not a traditional value, but it satisfies our criteria for an exponential function. B, the base, has to be a real number, and it has to be positive, and it can't equal 1. So this is fine. This is my value for B, the fourth root of 1/6. And then we go ahead and take that value and we substitute it in to any one of the original equations that had A and B, or any version that has A and B, and solve for A. So I have A was equal to 1 over B squared. So let's substitute in B. I have A is 1 over the fourth root of 1/6 squared. Well, that's 1 over, here I have 1/6, and then the fourth root is 1/4, and then times 2 in the exponent there. So 1/4 times 2, that's 1/2. So what I end up here with, I'm going to go ahead and scoot this over a little bit to make space. So I have 1 over 1/6 to the 1/2. So I have 1 over the square root of 1/6. And I can actually do a little bit more simplifying to that as well if I make myself even more space here, because this is 1 over the square root of 1 over the square root of 6. And so instead of dividing by a fraction, I can multiply by the reciprocal. So I get radical 6. So radical 1 is just 1, and so when I multiply by the reciprocal, it's just radical 6 over 1. So that's my value of A. So finding the equation of this exponential function is y equals, the value of A is radical 6 times the value of B was the fourth root of 1/6 to the x. The fourth root of 1/6 to the x. So this is my exponential function. In this next example, we're going to just evaluate exponential functions. So for part A, we have f of x equals 2 times 4 to the x for f of -2. So that means we substitute -2 into the value of x. So f of -2 is 2 times 4 to the -2. So once again, I cannot multiply the 2 and the 4. I can't multiply the a and the b value because first I have to handle the exponents. So first I have to think about 4 to the -2. Well, so in order to handle this, I have to first rewrite it so that I have a positive exponent. So the most common mistake here is for people to say 4 to the -2 is -16, which it is not. I have to get rid of the fact that I have a negative exponent. So we keep the 2 in the front, in the numerator, but 4 that's being raised to the -2 drops to the denominator and becomes 4 to the +2. So what I have is 2 over 4 squared, which is 2 over 16, which can reduce down to 1 over 8. And we always want to write all answers in lowest terms. And in part B, we have f of x equals -3 raised to the power of the quantity 2x minus 1 for f of 2. So we're going to plug 2 into our x. So f of 2, we have -3 all raised to 2 squared minus 1. So we're going to go ahead and simplify the exponent. 2 squared minus 1 is 4 minus 1, so that's 3. And then we go ahead and do 3 cubed first. So this negative is on the outside completely. We have to do order of operations first. So we have to do 3 cubed is 27. So we think about this as like a -1 times 27, which is now -27. So the common mistake here would be if there's a negative in the front to think that it's attached to the base. So the only way it's attached to the base is if there are exponents around, or parentheses around it, excuse me. But we can't have a negative in the base, right? So that's even more reason to help you recognize that that negative is really like a -1 being multiplied times the exponential piece. So we have -27 here. Now in this next example, we would want to evaluate using a calculator, and then we're going to round our answers to the thousandths place. So here I have 3 being raised to the 2.4. So this isn't something we can do by hand. We would need a calculator. And so I'm going to go ahead and just show a picture of a calculator for a second. So this is a TI-36X Pro. And if you are looking for a way to get to the exponent, in this case it would be this little button that's X and then with a little box in the upper right hand corner. That will take you to the exponent location so that you can go ahead and enter in 3 to the power of 2.4. On other calculators, it will be a symbol that looks like a little upward arrow. So for some calculators, you're going to press 3 and then a button that looks like an upward arrow, which is called caret, and then 2.4. So go ahead and practice that on a calculator, and you will get approximately 13.967, and we are rounding to the thousandths place, which means that we are going to 3 places past the decimal. So it's important to know your place values. Next we have 6 to the negative 1.2. So here we want to just go ahead and use our calculator again and make sure that you use a negative instead of a minus. So going ahead and viewing a calculator again, there is typically a button that is negative, which has little parentheses around it indicating negative, as opposed to the subtraction symbol, because then you will get an error if you use subtraction instead of a negative symbol. And typically the negative is smaller, shorter in length than the subtraction symbol. So if you enter this into your calculator, you get 6 to the negative 1.2 is approximately 0.116 if I round to the thousandths place. And then in part C, we're looking at e to the 3.4. Now, what is this e? E is an irrational number. The irrational number e is called the natural base. And e actually can be approximated by 2.718. But since it's irrational, it keeps going on forever and ever and ever. So this is just an approximation, and we would not want to use an approximation to find e to the 3.4 because we have our calculator. And there is a special button on a calculator for finding e to a power. So here I have a button that's e to a power. I know this is really small, but there is typically an E button, usually off to the left-hand side, and sometimes you'll see E to the little power. So if you have that, E to, in this case, 3.4, you will find is approximately 29.964. So this is really just a matter of getting familiar with your calculator. You can have any scientific calculator, and if you are struggling finding these particular values, please come and work with me so that we can make sure you know how to use your calculator, especially when it comes time for the exam. The next big thing I want to point out is that since we are rounding, I did not use equals, I did use an approximately symbol, which is important. And then one more time, it is important to know your place values. So we have the tenths place, the hundredths place, and the thousandths place. So thousandths is 3 places past the decimal. Now we're going to switch gears and talk about graphing exponentials. And we're going to start by looking at the graph of e to the x. So the function f of x equals e to the x is the natural exponential function, because we just learned that e is the natural base. Now it passes through the point 0, 1. So if we again think about plugging in 0 for x, any number to the 0 is 1. So we have it passing through the point 0, 1. So this is my graph of e to the x. We can see that it passes through the coordinate point 0, 1. Another coordinate point that it passes through is 1e. So if I plug in a 1 for the value of x, I get just e to the 1, which is e. And we said e was about 2.7. So here I want to go ahead and draw attention to the point 1e, because this is 1 and then about 2.7 approximately. So that's why I can see the y value is between 2 and 3. And I also have a horizontal asymptote at y equals 0. So y equals 0 is a horizontal asymptote. I am approaching, but actually never going to cross this particular horizontal asymptote. So this is the graph of y equals e to the x, and we're considering it a parent function now. So we're going to go ahead and graph y1, which is e to the negative x minus 2, all that's in the exponent, and then plus 1. So we're going to go ahead and think about this using transformations, but there's one little piece that we have to go ahead and talk about. So the way that this is written currently, I have e to the negative x minus 2. So what I have to do is I have to factor out a negative there. So I have negative and then times the quantity x plus 2. So when we think about something as with the x, quote unquote, it needs to be with it in the sense that it's in parentheses or underneath a radical. So here I did need to think about taking out the negative. So I have e to the negative and then the quantity x plus 2, and then on the outside I have plus 1. And that was important to do because then that would change our shifts. So let's go ahead and discuss all of our transformations. Well, the negative is next to the x value as opposed to in the front of the function. So we're going to have this be a reflection over the y-axis. So reflects the y-axis. The plus 2 is going to shift me left 2. And the plus 1 on the outside is going to shift me up 1. So let's go ahead and think about the reflection first. So the reflection over the y-axis will keep 0, 1 right on the y-axis, but 1e is going to flip over to negative 1e. And then I'm going to go ahead and have, now instead of an increasing function, I'm going to have a decreasing function, but I'm just going to go ahead and sketch it as a dotted function because it's not the final graph. And then all at once, I'm going to shift everything left 2, up 1. So I'm going to go ahead and switch myself to a different color, and then I'm going to go ahead and go left 2, up 1. So first I'll move 0, 1, left 2, up 1. And then I'll go ahead and move my negative 1e point. So I'm going to go left 2, and then up 1. So I want to be at about negative 3 and then 3.7. So the other thing that moved up is the horizontal asymptote. So since the horizontal asymptote was y equals 0 right on the x-axis, now it's moved up 1 unit. So I'm going to go ahead and sketch a horizontal asymptote, and that's just going to help right now when I go ahead and sketch my graph. So I'm going to go ahead now and connect these points with a decreasing function that's going to approach my horizontal asymptote. So still a lot of the basics that we talked about before in terms of the transformations of a graph, but now we're just adding a new parent function, e to the x. And this is definitely the most well-known exponential function, and the one that we're going to continue to see, you're going to continue to see if you move throughout future math classes. Now let's take a look at graphing exponential functions more generally, where we have y equals a times b to the x. Well, there's two situations. I could have exponential growth or exponential decay. Exponential growth refers to an increase based on a constant multiplicative rate of change over equal increments of time. In other words, this is a fancy way of saying that the base b has to be greater than 1. I'm going to be multiplying by a number greater than 1 every time. That's going to cause an increase. And graphically, we can see this would be an increasing function. So in other words, this particular graph might represent the function y equals 3 to the x, because the base is bigger than 1. So every time to get from one value to the next, I'm multiplying by 3. So my values are getting bigger and bigger. I have exponential growth. And then notice here, I'm passing through the point 0, 1, because if I plug in x equals 0, anything to the 0 is 1. And then I have exponential decay if I have a decrease based on a constant multiplicative rate of change over equal increments of time. So this is a fancy way of saying that b is between 0 and 1. So a number like a fraction between 0 and 1. In that case, I have what looks like a decreasing function, and we call this exponential decay. So this particular graph might have the equation y equals 1/3 to the power of x, because 1/3 is a base between 0 and 1. So every time we're multiplying by a third, that makes our function smaller, because multiplication by a third is division by 3. So that's why as I continue to go up by equal increments, my y values are getting smaller and smaller. And then again, if I plug in 0, anything to the 0 is 1. So both of these graphs have in common that they pass through 0, 1. And that's because their a value is 1 in both cases, but we never really write that 1. The other thing they have in common is note that both graphs have a horizontal asymptote at y equals 0, which is of course the x-axis. In this example, let's go ahead and identify the parent function and graph it by plotting points. Then identify in words and apply the transformations to the graph of f of x. Find the domain, the range, and any asymptotes of f of x. So here we have in part A, f of x is negative 2 to the x plus 3. So my parent function here is the function 2 to the x. And to graph 2 to the x, we should remember this is going to be exponential growth, an increasing function, because 2 is greater than 1. And what we can always do is just think about plugging in points. And the easiest values to plug in are going to be 0 and 1. So if I think about creating a little table of x and then y equals 2 to the x, if I plug in 0, well, anything to the 0 is 1, 2 to the 0 is 1. If I plug in 1, I get 2 to the 1, which is just 2. So I have the point 0, 1 and the point 1, 2. And from here, it's just a matter of now remembering that this is exponential growth. I'm going to have an increasing function. I'm going to draw it as a dotted function because it's not my final answer. I have an increasing function with a horizontal asymptote of the x-axis. And from here, we want to identify our transformations. So a negative that's multiplied in the front of the function is going to reflect me over the x-axis, so reflects the x-axis. And then we're going to go ahead and move everything up 3 units. So first we'll go ahead and reflect over the x-axis. So we have 0, negative 1. We have 1, negative 2. And so we'll go ahead and flip this over. And then we'll move everything up 3 units. Well, the flip didn't change the asymptote. I was still having an asymptote of the x-axis, but if I move everything up 3 units, the horizontal asymptote will move up 3 units as well. So I'm going to go ahead and redraw my horizontal asymptote at y equals 3, and then I'm going to move my points up 3 units. So I'm going to be at 0, 2, and then I'm going to be at 1, 1. And then I'm going to go ahead and connect those points with my solid graph this time, because this is going to be my final answer for my graph of f of x. Now the last part is to find the domain, the range, and any asymptotes. So let's go ahead and just label the asymptote. We said the horizontal asymptote was y equals 3. Remember to write it as y equals, not HA equals. The domain, well, the domain of any exponential function is negative infinity to infinity. I can see this graph will go left forever and right forever. But the range, based on the graph, will go from negative infinity, so since this is going to go down forever, but it's going to approach and never cross this horizontal asymptote of 3. So we have negative infinity to 3, open, positive 3. Open. So I'm going to approach positive 3, but I'm never going to cross it, so I have to put open parentheses around 3. And in this last example, we have the same set of instructions, but a new function to graph. F of x equals 2 times 1/3 to the x minus 1. So my parent function this time is going to be 1/3 to the x. Y equals 1/3 to the x. So that's going to be exponential decay. And so what we want to think about is just plugging in a couple of values. So I'm going to go ahead and think about plugging in some x values into 1/3 to the x. This time I'm going to plug in -1, 0, and 1. So if I plug in -1, I get 1/3 to the -1. And what that negative is going to do is it's going to flip my fraction. So I'm actually going to get positive 3 over 1 instead of 1 over 3. And if I plug in 0, anything to the 0 is 1. And if I plug in 1, 1/3 to the 1 is just 1/3. So we have that typical 0, 1 point. If we were to have just plugged in 1, we'd have 1 1/3. And I mean, that's fine in general, but ideally we would like a point on the other side, especially with this decreasing function. So if we plug in -1, we got out 3. So now I can really see I have this exponential decay going on. So I'm going to go ahead and connect those points together, make this a dotted function that approaches the x-axis. And then we'll go ahead and address the transformation. So the 2 in the front is going to be a vertical stretch by 2. So it's going to affect my y values. My y values are going to double. And then the x minus 1 is going to shift me to the right 1 unit. So here I'm going to go ahead and remember this is the point -1, 3, this was 0, 1, and this was 1, 1/3. Because with a vertical stretch, my y values double. So that means that I'm going to have, instead of -1, 3, I'm going to have -1, 6. Instead of 0, 1, I'm going to have 0, 2. The y value will double. And instead of 1, 1/3, I'm going to have 1, 2/3, which is super close because my points are kind of big here. So this is going to be the vertical stretch applied. And then finally, everything's going to shift right 1 unit. So my final graph here will have me passing through 0, 6, 1, 2, and then 2, 2/3. And then I'm going to go ahead and connect those together with a solid graph. And also recognize, since I didn't actually have a shift up or down, my horizontal asymptote didn't change. So when we go ahead and label all of our pieces here, because we need to identify any asymptotes, we still have a horizontal asymptote of y equals 0. We have a domain from -infinity to infinity. And our range this time will be from open 0 to infinity. So my lowest y values are going to be near 0, but never crossing the x-axis. And then I'm going to go up to infinity there. So here, when we're graphing our parent functions, we can go ahead and plot points. Here I went ahead and plugged in -1, 0, and 1. And those are 3 ideal points to plug in. When it was +2 to the x, I just went ahead and plugged in 0 and 1, but we could have absolutely plugged in -1 as well, just to give us that more accurate parent function, because then we do have to go ahead and apply our transformations to those points.